Okay, so we'll go to the next problem. So the question is again the same question like the previous problem. Determine the reaction forces at all contact surfaces. Determine the reaction forces at all contact surfaces. The given that are, this is ball 1, this is ball 2. So ball 1, radius of the ball is 20 millimeters, weight is 100 newtons. Ball 2, radius is 30 millimeters and weight is 300 newtons. Overall width of this trough or rectangular channel is 90 millimeters. Okay, so we need to find the reaction forces at all contact surfaces. So the first step is to mark the contact surfaces. So let this be, first is one contact surface here, the other is here, one is here, one is here. Totally 1, 2, 3 and 4 contact surfaces. I will call this as P, I will call this as Q, R and S. Okay, P, Q, R, S. Totally 4 contact surfaces. I have named it as P, Q, R and S. Okay, so now first we need to consider the free body diagram. What is free body diagram? The diagram of the body in which body under consideration is freed from all the contact surfaces and shown with the forces acting on it. Okay, so now you can see here I am considering the free body diagram. So let this be your lower ball. One second, yeah, let this be your lower ball. Okay, and let it be your upper ball. Okay, so let it x-axis and let it be your y-axis for lower ball. Let this be x-axis and this be y-axis for your upper ball. Okay, now so you can see here at joint P or here a perfectly vertical contact surface. So at every contact surface there exists normal reaction which is acting perpendicular to the contact surface. So here perfectly vertical means perfectly horizontal normal reaction. So this is the reaction force. I will call this as RP. Similarly at R also a perfectly vertical contact surface, perfectly horizontal normal reaction will be acting like this. So remember here we are drawing the reaction forces. This ball tried to push the wall and gets the same back. This ball tried to push this wall and gets the same back. We are drawing the reaction forces. Again perfectly horizontal contact surface, perfectly vertical normal reaction. I will call this as RS. Okay, and other than that weight is acting vertical downwards here, so I will call this as weight. Here weight is given as 300 for upper ball and here the weight is given as 100 for lower ball. Okay, so RS is acting vertical upwards here, weight is acting vertical downwards. Now here at joint Q or at contact surface Q, okay, we need to draw the reaction forces. So we don't know at what angle it is acting, that is RQ is acting. For that what I will do, so again the same procedure for the same as the previous problem. First join these two lines, that is centers of the circle. Now this is the radius of lower ball, this is the radius of upper ball. Okay, now from here draw a perpendicular and from here draw a line to the perpendicular erected. Now I will call this as theta. So let this be small a, small b, small c. Okay, so you can see here I am drawing the triangle here. This is a, this is b, this is c, this is perpendicular, this is theta. Okay, what is AB? AB is radius of lower ball plus radius of upper ball. Radius of lower ball is 20, this is 30. 20 plus 30 is 50. So this is 50. Okay, now what is AC? Again AC is equal to how much? So AC is total width, okay, minus radius of lower ball minus this. This is equal to what? This is equal to this. This is nothing but radius of the upper ball. So it is AC is 90 minus R1 minus R2. So cos theta is equal to adjacent by hypotenuse. Adjacent is 90 minus R1 minus R2. 90 minus 30 minus 20. 90 minus 30 is 60. 60 minus 20 is 40. Okay, so this is 40 divided by 50. So theta is equal to cos inverse 4 by 5. Shift cos inverse 4 by 5. The answer is 36.86. So it is theta is 36.86. That means this at this point RQ is acting at an angle at theta with respect to horizontal. Now you can see here this ball tried to push this ball and gets the same back. Here we are drawing the reaction forces. That means RQ is acting like this here. This is the angle theta. Theta is equal to 36.86. This is for RQ for this ball, and for this ball tried to push this ball upwards and gets the same back. So here we are drawing the reaction forces. This is the angle theta. Okay, this is the free body diagram. Once you draw the free body diagram, next we'll consider each body separately. We'll draw the coordinate system and then we'll apply the equations to get the reaction forces. Okay, so here I am drawing a line. 1 second. Yeah. Now first I will consider upper ball. Okay, first I will consider the upper ball. Okay, so for upper ball, let it be your x-axis, let it be your y-axis. Okay, now you can see here for upper ball, RP is acting like this. It means it is acting through positive x-axis but actually acting in the negative x-axis. So this is the direction of RP. 300 acting vertically downwards, so 300 acting vertically downwards, you can see here. And then RQ, where RQ is acting, you can see here RQ is acting passing through third quadrant but actually acting in the first quadrant. Angle is theta with respect to horizontal, so you can see here this is your RQ. Angle is theta with respect to horizontal, theta is 36.86, right? Now 1, 2, 3, as there are only 3 forces, you can see here 1, 2 and 3. 1, 2 and 3. As there are only 3 forces, we can apply Lami's theorem, or else you can apply summation of x and summation of y. So I'm drawing here, sorry, I'm using Lami's theorem according to Lami's theorem. Okay, first I will consider 300. 300 divided by angle between other 2 forces. That means I want this angle. 1 second. Yeah, I want this angle. So you can see here this angle is equal to how much? From here to here, this is 180. 180 minus 36.86. So 180 minus 36.86, the answer is 143.14. so I will sign 143.14, that is equal to, okay, now we'll consider RQ force. Once you consider RQ force, angle between other 2 forces, RP and 300, so we can clearly see here it is 90. Sin 90 is equal to RP divided by angle between other 2. So you can see here from here to this is 90. 90 plus 36.86, 126.86. So sin 126.86. So 143.14 plus 90 plus 126.86. The answer is 360. So this is correct. Okay. Now RQ is equal to and RP is equal to. First equate these two, get the value of RQ. Then equate these two, get the value of RP. Okay, so RQ is equal to 300 into sin 90 by sin 134, and RP is equal to 300 into sin 126.86 divided by sin 143.14. Okay, so RQ is equal to 500 newtons and RP is equal to 400 newtons. It is 500, it is 400. We got the value of RP and RQ, that is RP and RQ. RP and RQ. Now we'll consider the lower ball, okay, and then we'll find the value of RR and RS. This is RR. This is RR and RS. Okay. Okay. Now we'll consider the lower ball. Okay. So we'll draw the coordinate system. So I'm drawing here the lower ball. Okay. For lower ball, or you can say the smaller ball. Okay. Let it be your x-axis. Let it be your y-axis. Okay, now you can see here RR is passing through negative x-axis but actually acting in the positive x-axis, so I will rename it as RR. Okay, then RS acting vertically upwards, so RS is acting vertically upwards, and 100 Newton acting vertically downwards or along negative y-axis, so this is 100 newtons. And then for this RQ is passing through the first quadrant but actually acting in the third quadrant. Angle of inclination is theta with respect to horizontal, so let this be RQ. This is theta with respect to horizontal. Okay, so now theta is equal to 36.86. we know the value. Okay, now there are 1, 2, 3 and 4 forces, so we can't apply Lami's theorem. We have to use summation of x equal to 0, summation of y equal to 0, that is equations of equilibrium. So first condition, I will use summation fx equal to 0. Summation fx means addition of x component of all the forces. RR is acting purely along x axis, its y component is 0, acting in positive x axis, that means plus RR. RS acting along positive y axis, its y component, x component is 0. RQ acting in the third quadrant, x component is negative. First we'll put negative sign. So theta with respect to x axis means x component is cos. So RQ cos theta, theta is 36.86. And 100 Newton acting along positive negative y axis, that is purely along y axis, there is no x component, so that's equal to 0. So from this, RR is equal to RQ cos 36.86. value of RQ is 500, so 500 cos 36.86, it is 400, so RR is equal to 400 newtons. And second condition, summation Fy equal to 0 or summation of vertical forces is equal to 0. You can write both. So summation Fy means addition of y component of all the forces. If you consider RR, it is purely acting along x-axis, y component is 0. RS acting along positive y-axis, so I will write here plus RS. RQ acting in the third quadrant, y component is negative, so minus. Component is theta with respect to y, x-axis means x is cos, y is sin. So RQ sin theta, theta is 36.86. 100 acting along negative y-axis only, so minus 100 is equal to 0. From this condition, RS is equal to 100 plus 100 plus RQ. RQ is 500, so 500 sine 36.86. The answer is 399.9, or you can say 400. So it is also equal to 400 newtons. So we got all the reactions, that is RQ, RP, RQ, RR and RS. So RQ is equal to RP is equal to 400, RQ is 500, RR and RS as 400. So we got all the reactions, that is RP, RQ, RR and RS. Okay, this completes the problem. Here understanding of this free body diagram is very much important in this type of problems. So I have explained you 2 times. In the previous problem also, here also. Once again I will explain here. So first we'll consider the free body diagram of both the balls. So what is a free body diagram? The diagram in which the body under consideration is freed from all the contact surfaces and shown with the forces acting on it. So first the lower ball and the upper ball. Now you can see here perfectly vertical contact surface, that means perfectly horizontal normal reaction, because at every contact surface there exists a normal reaction which is perpendicular to the contact surface. So this is RP. Now similarly weight is acting downwards, and now at point RQ. Okay, so we don't know the at what angle the RQ is acting with respect to horizontal. For that we'll join these two, and then from here we'll draw a perpendicular, we'll join this, we'll consider this triangle. Now this AB is equal to this radius plus this radius, so we got this here, and AC is totally 190 minus this. This is my radius of lower ball and this is radius of upper ball, because this is parallel to this. Okay, so we got the theta as 36.86. Now this, as we are drawing reaction forces, this ball tried to push this ball downwards and gets the reaction back. Okay, and gets the reaction back. So this is RQ. 1 second. Okay, and gets the reaction back. So RQ is acting like this. You can see here RQ is acting like this. Where RQ is acting now? It is passing through third quadrant and acting in the first quadrant. Theta with respect to horizontal. So you can see here theta with respect to horizontal. Okay. Now similarly for this ball, RR is at RR a perfectly horizontal normal reaction here and perfectly vertical normal reaction here. Weight acting vertical downwards. Now this ball tries to push this ball upwards and gets the reaction back. So this is a reaction. Okay. Now theta with respect to horizontal. After that we'll consider the coordinate system. We'll draw the and we'll apply the equations to solve the problem. Okay.